3 more minutes to go. Hello, hello, Professor. How are you?
Yeah, fine.
All.
Hello, Jürgen. Hi.
Hi. You all interrupted dinner or have it already?
No, not yet. For me, it is not yet. I had booster recently.
Oh, you got a booster. Yeah. Right.
What's hardest for Steve? I think it's 7 in the morning, or what is it in California?
It is 7 in the morning. Yeah.
You are in Washington, right?
I'm on sabbatical this year at Caltech.
Oh, in Caltech. Okay. Cool.
Yeah. So normally it would be in Washington.
Yeah.
But I do think 7 in the morning is easier for me than 9 at night or 10 at night.
Hello.
Hello. Hi.
Easier for me than 9 at night or 10 at night.
Okay. Prof. Kutz, I will introduce the speaker. Is that okay?
Yes, of course. You know him much better than me. Please.
Okay, so good day, everybody. People are there from California to Japan, and I'm really happy to host the seminar, Critical Transition Complex System, the seminar series or webinar series being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research in Germany. This seminar series brings together experts in a variety of fields like climate science, combustion, neuroscience, fluid mechanics, and aims to disseminate the state of the art in the prediction of critical transitions and in these diverse fields of study. And we hold the seminar in the last Monday of every month, so mark your calendars. Before I introduce the speaker, a few housekeeping notes. One, I request everyone to turn off their microphones, and the audience can make use of the Q&A box at Zoom to ask the speaker your questions. We will have time at the end of the talk to discuss these questions and clarifications. And with that, let me introduce the speaker today. Dr. Stephen L. Brunton is a professor of mechanical engineering at the University of Washington. His research combines machine learning with dynamical systems to model and control systems in fluid mechanics, biolocomotion, optics, energy systems, and manufacturing. Among his numerous achievements, I list only a few. He's the recipient of the Army and Air Force Young Investigator Program Awards and the Presidential Early Career Award for Scientists and Engineers. He has also co-authored 3 very popular textbooks, which are now become standard textbooks for data-driven science in the fluid mechanics community. And today he'll be presenting a talk on machine learning for scientific discovery with examples in fluid mechanics, which is a very interesting subject. And we have the upcoming speakers. The next seminar will be given by Dr. Louis Picora, a pioneer of chaos control, on 28th February, the last Monday of next month. So with this, I will stop and I give the floor to Steve.
Wonderful. Thank you so much for the kind introduction and also for the invitation to present at the seminar series. So it's great to see everyone. And I'm really excited to tell you about some of the work going on in my lab and with my collaborators in this interesting field of machine learning for scientific discovery. So I'm just going to jump right in. But before I do, I want to acknowledge my many excellent co-authors, colleagues, and collaborators in this work. Ranging from applied math to fluid mechanics and kind of everything in between. And I especially want to acknowledge my wonderful postdocs and students in the middle row who have done most of the work I'm going to tell you about. So one of the things I like to start off in these seminars is to give my perspective on how machine learning fits in with classical dynamical systems and control. So at heart, I really consider myself a dynamical systems person. All of the systems I care about, like fluid flows, neuroscience, disease modeling, climate, these are all high-dimensional, nonlinear, multi-scale dynamical systems. And the tasks in blue that we generally face in dynamical systems modeling, like reducing the dimensionality of a fluid simulation with 1,000,000 degrees of freedom, or modeling the coevolution of coherent structures or patterns in a complex system, optimal sensing, estimation, and control. All of those tasks are very naturally posed as challenging optimization problems in pink. And they're challenging specifically because the physics of the system at hand are multi-scale and nonlinear. Okay, there's multi-scale structures in space and time, there's nonlinear evolution dynamics, and that gives rise to very high-dimensional non-convex optimization problems. And for decades, if not centuries, those have been kind of the main challenges facing us in dynamical systems research is high-dimensional, nonlinear, multi-scale dynamics. But I want to point out that machine learning is getting really, really good at solving these kinds of high-dimensional, non-convex optimization problems. Think about training a neural network. That's exactly the kind of high-dimensional, nonlinear optimization we're talking about. It has multiple kind of non-convex optima in the landscape. And so I like to oversimplify and say that machine learning is essentially building models from data using optimization and applied regression. And of course, there's a lot new happening because we have faster computers and tons more data, better applied math algorithms. But if you think about it this way, building models from data is something we've been doing for decades. I'll go back to Kalman in the 1950s and 60s, building models from data. And you can go back centuries if you like to find examples of this in science. Now, why do we believe that we can apply these techniques to very, very complex systems like, turbulent fluid flows and to understand the brain? And I would argue that the reason is because patterns exist in your data. So patterns existing in your data is why we've been able to do complex analysis in fluid mechanics for the last 5 decades. It's also why we believe we can use machine learning to understand these tasks. And I'm going to give you examples in fluids. I love fluids. They're very photogenic. But you can think of any complex, high-dimensional, nonlinear, multi-scale system you like, and it probably applies pretty much the same. And if you're interested in how to extract these dominant coherent patterns in your fluid flow systems, there's this great review paper by Sam Tyra from 2017 on how to kind of decompose fluid flows into a minimal modal basis from data. Okay, good. Before I jump into some technical matter, I want to give you an overview of what we do in my lab. And so this is kind of the diagram I use to organize the research that happens in my lab. Everything I care about is up in this blue box of dynamical systems. Again, this could be your brain, a network of 100 billion neurons working together, or it could be a turbulent fluid flow over a jet wing or through a jet engine. It could be how a disease rips across a continent through the population dynamics. And so a huge part of my lab, probably over 50%, is focused on building models of these dynamical systems purely from data. So you could call this system identification if you like, but really the goal is to build interpretable, generalizable models, differential equations that describe this data that is observed in the most physical way possible. And here, what I mean by physical is that if we train our models on a subset of data, we want them to be able to generalize to other phenomena we haven't seen yet. Another big part of my lab deals with directly learning good control laws from data. So bypassing the modeling perhaps, and instead learning through trial and error, maybe how a biological system would learn to interact with a complex environment. And so this is related to things like model predictive control, reinforcement learning. Sometimes we use genetic optimization. But the idea is through trial and error, through experience, to push on a system of interest to find out good ways of manipulating it for some engineering advantage. This picture here shows a cross-flow turbine example we've been working on for a number of years now, where we have used relatively simple optimization techniques to harness unsteady fluid dynamics and extract considerably more power from these systems than using kind of industry standard control techniques. And then the third big leg of this work is in sensor and actuator placement. So all of modeling and control is prefaced on having a good set of sensors and actuators. But again, in very high dimensional systems, it's not always obvious where to measure and where to actuate. So if you are Boeing or Airbus, it's not obvious where you would put 5 sensors on a wing for some objective. And so this is actually work I do with my spouse, Bing Brunton. She is a neuroscientist, and we work together to try to understand sensor and actuator placement in the context of biological systems. So these flying insects have on the order of 10 to hundreds of strain-sensitive neurons distributed on their wings, visualized some of them in these red dots. And they use this information to inform their flight control system. And so we want to kind of reverse engineer these insects to understand why they place sensors where they do, and how we can develop algorithms for sparse sensor placement in our own engineering systems. So that's the big picture. And today I'm specifically going to talk about this block here of building interpretable generalizable models from data. Okay, good. Now, I always love to kind of get everyone on the same page about what kinds of machine learning models we want for lots of safety critical applications. So, I work with companies that develop aircraft and engines, self-driving cars. If you get on an airplane or into a self-driving car that is using machine learning algorithms, we should be asking for machine learning algorithms that are interpretable and generalizable. Now, I always get into fights when I try to define these rigorously. So I'm just going to give you my favorite example of an interpretable generalizable model, which is Newton's second law, F equals ma. So this is clearly highly interpretable. It has 3 terms: force, mass, and acceleration. They have units. You can write them down for a particular problem of interest, like a pendulum or an aircraft. And you can go and communicate them with a friend. You can analyze them. You can solve these differential equations. They're highly interpretable. They're generalizable in the sense that you can learn F equals ma from an apple falling on Earth, and it's still valid when we land humans on the moon. That's like the ultimate generalizable model. Okay, that's the kind of thing we would dream of having with our machine learning models, is this kind of generalizability. You train it over here on Earth with apples falling, it's still valid when you land humans on the moon. Now, you could train a neural network on videos of apples falling. If you had 1,000 videos of 1,000 apples falling, you could build a deep neural network that would learn to make new videos of new apples falling. But that would not be valid or useful when we decide to land humans on Mars. Okay, so I want models more like F equals ma. And this is not just Newton's second law. This has been a principle of parsimony from Aristotle to Einstein. Essentially, this has been the gold standard in physics for millennia, is this idea that the bits that are physical, the bits of a model that generalize, and that's a pretty good working definition of physics, is models that generalize, are typically found because they're the models that are as simple as possible, but no simpler. That's the principle of parsimony. That's Occam's razor. And so in the mathematical era today, all of us have a few tools at our disposal to promote models that are more interpretable and generalizable, more physical models. And for me, at least, those are low dimensionality and sparsity. I want my model to be described in terms of as few variables as possible, low dimensional. Maybe these describe coherent structures in a fluid. And I want a differential equation describing the coevolution of those variables that's as sparse as possible. And so this is a kind of cartoon that I use and my group uses to organize our thoughts around this. We want differential equations like z dot equals f of z that are sparse, that have as few terms as possible. But we might measure our system in some original coordinate system X, which is high dimensional. Maybe it's a confusing coordinate system. Maybe I have a video camera or an iPhone movie of some physical system, and I need to learn some good coordinate system Z where my dynamics f of Z are sparse. So a lot of what I'm going to tell you about is how do we learn those coordinate transformations phi, and how do we learn the differential equations Z. Okay, so if we fast forward from Newton to the computational era now, the kinds of models I want look a lot like this Lorentz 1963 model to describe chaotic thermal convection. So you'll notice that this Lorentz model on the right has the two ingredients I described earlier. It's low dimensional. This model is in terms of three variables, X, Y, and Z, that are the modal amplitudes of three spatial modes that are co-evolving. And the dynamics are sparse. Out of all of the possible right-hand side dynamics, out of all of the differential equations that could describe this, these are extremely simple. They have 7 terms and 5 of them are linear. So that's the kind of models we're going to develop. And for the next part of this talk, I'm going to show you how we have automated kind of this Lorentz 1963 modeling perspective. Good, so I'm actually going to show you our algorithm on the Lorentz system. Okay, so we call this the sparse identification of nonlinear dynamics, the SINDy algorithm. And we're going to warm up or test this out on data from the Lorentz 1963 system. Now notice, we are already measuring our system in the good coordinates X, Y, and Z. So that's a huge burden that's been lifted, is that we just assume we measure the right coordinates X, Y, and Z, and we can compute derivatives. By far, the simplest thing we could do to model would be to build a linear regression model that best fits X dot, Y dot, and Z dot in terms of a linear combination of the columns X, Y, and Z. This is essentially what the dynamic mode decomposition does. It gives you a little 3x3 A matrix that best fits these dynamics. Now, I don't think any of us believe that a 3x3 linear system is going to give us the rich dynamics of the Lorentz system with multiple fixed points, unstable periodic orbits, and chaos. And this is almost a cartoon of why DMD often fails when applied to really complex systems that are not just periodic or quasi-periodic. So instead, what we're going to do is augment our right-hand side to include more terms that could describe the dynamics. In this case, I've chosen polynomials, x squared, xy, y squared, all the way up to 5th order polynomials, z to the 5th. But you can choose anything you like, Bessel's functions, sines and cosines, rational functions. It's only up to your imagination how you build this library theta. And now the objective is to find the fewest columns. Remember, we want simple models, sparse models. So we want the fewest columns of theta that add up to x dot, that add up to y dot, that add up to z dot. 20 years ago, this would have been a brute force combinatorial optimization to find these sparse combinations. This would not have scaled with Moore's law. This would have been computationally intractable. Now, today, after advances in the 1990s in robust statistics, this is a commodity algorithm. In fact, there are a dozen commodity algorithms for sparse regression that will give you the sparsest combination of theta that adds up to x dot. And you'll notice that the terms that are highlighted in blue and red and green are exactly the terms that were in the original dynamical system that generated the observed data. So this shows that it is possible in some circumstances to do truly nonlinear system identification, to learn the structure and parameters of a nonlinear differential equation purely from measurement data. We only measured x, y, and z. We didn't know what the equations were in this identification process. Okay, so that's an overview of SINDy, illustrated on a toy example where we totally already knew the answer. If you want to try this out for yourself, we have this PySINDy code in Python. It's been pretty well maintained for the last few years by our grad students and postdocs, but also by the wider community. So I'd say this is a pretty good resource if you want to try this out. Now, the next perspective here is that we can also use this not just to model ordinary differential equations, but to model partial differential equations as well. So this is work by Sam Rudy when he was a PhD student working with Nathan Kutz and myself, where we took data from a fluid flow example, this flow past a cylinder, kind of a classic example, and we assumed that we could measure the full spatial fields resolved in time. And in doing so, we can generalize our SINDy library regression procedure. So now our library of candidate terms in the nonlinearity includes partial derivatives and nonlinear products of partial derivatives. So subscript is partial derivative. Omega sub x is the x derivative of vorticity. And you can do the same thing. You can build all of this from measurement data, and then you can apply the same sparse regression algorithm to learn what the fewest partial differential equation terms are. And our identified dynamics are, in fact, the Navier-Stokes equations. So what we learn here is that the sparsest, the most parsimonious model that describes the observed data is, in fact, the Navier-Stokes equations for fluid flows, which is what we expect, because that's clearly the equations that generated the data. Now, at this point, you should be saying, well, look, Steve, you knew the Navier-Stokes equations. In fact, you probably used them to simulate that data to rediscover the Navier-Stokes equations. And that's certainly true. Whenever you develop a new machine learning algorithm, I highly recommend applying it to a system where you know the answer so that you can get some understanding of how the method is working. But since introducing this variant of SINDy, our group and colleagues across the world have been applying this to systems where we do not know the answer, where we don't have a partial differential equation. So the two most interesting examples I've seen are in plasma physics. So in plasma physics, we have the magnetohydrodynamics equations, but they're not nearly as perfect of a model as incompressible Navier-Stokes are. And so what researchers are doing is essentially discovering partial differential equations with more or less terms in the model than the classical MHD equations. And that's giving them hypotheses about new mechanisms, new physical mechanisms that can drive those complex observed dynamics. The other example I've seen this applied to is in active matter, which is really cool. So think of non-Newtonian fluids. Maybe you have blood going through your veins or filament flows. You can learn things like the Navier-Stokes equations, but again, that have additional nonlinear terms for additional physical mechanisms. And I'll just point out as an aside, because the data for spatial temporal systems is typically vast, there's a ton of data, you can often get away with massively subsampling the system, and you still typically have enough data to learn good dynamics. Okay, I want to take a step back and summarize what we've done so far before we move to the next step of the talk. So the goal of the SINDy algorithm is to learn dynamical systems from data. And specifically, I want dynamics that are interpretable, generalizable, that we can talk about like humans. This is what I mean when I say scientific discovery. I want models that are still amenable to human analysis. So for example, I might want ordinary differential equations or partial differential equations. If I start with data from the Lorentz system, I want to get something that looks kind of like the Lorentz equations, sparse dynamical systems in terms of a low dimensional variable set. If I have fluid flow data, spatial temporal data evolving, I might want to learn what partial differential equation governs that observed physics. And there's a third perspective I want to tell you, and I'll talk about that now, which is the reduced order modeling perspective. If I have that observed fluid flow, I might not just want a partial differential equation describing it. I might want to decompose that flow into a low dimensional basis. Maybe I have 3 orthogonal modes, the amplitudes of which are x, y, and z, and I might want a differential equation in terms of those modal amplitudes. For those of you who know your Lorentz 1963 history, that's exactly what Lorentz did, is took a high dimensional system and wrote the dynamics in terms of a low dimensional basis in terms of 3 variables. So this lowest row is what I'm going to talk about next. And this is what we describe as reduced order modeling. So this is flow field footage from my collaborator Richard Siemens' lab in TU Braunschweig. And the idea here, this is a very turbulent kind of complex flow. What we want to do is extract a few coherent structures, a few variables that describe the dominant patterns in this flow field, of which you can see with your eye, there are patterns. And then in terms of that low dimensional vector x, we want to model the dynamics with a sparse differential equation. So I'm going to warm up with this flow past a cylinder problem because it's one of the canonical problems we understand very well. And all the way back in 2003, Bernd Nowak and friends told us that there was a good coordinate system in terms of 3 variables to describe this system. You can use the first 2 proper orthogonal decomposition modes, POD 1 and 2. For those of you who are not in fluids, this is the same as the principal components analysis or the SVD. And then a third orthogonal mode called the shift mode, which is just the difference between an unstable fixed point and a steady mean flow. And if you write your dynamics in this coordinate system, if you take and expand the flow field in terms of these 3 variables, and you plug these into the Navier-Stokes equations and Galerkin project, you get a system of 3 differential equations out in blue. This is what Bernd Nowak did in 2003. And this is a famous paper because this is a very simple model to describe these observed dynamics. So we thought this would be a good test problem for our system. We measure this flow past a cylinder in X, Y, and Z coordinates. And instead of plugging this into the Navier-Stokes equations, which requires having a working code and intrusive kind of, it takes a lot of human time to get inside of the code to do this procedure, we just take the time series data of X, Y, and Z and apply our SINDy algorithm. And when we apply our SINDy algorithm, we essentially learn the structure of the original Nowak-Galerkin model, but without having to have a working fluid code or any invasive algorithm design. And our system captures the same general phenomena observed in the high-dimensional system, where we have a slow parabolic manifold and kind of the same timescale separation as before. Now, within 2 weeks of putting this paper on the archive, I got an email from Jean-Christophe Loiseau from Paris Tech saying that there were some kind of key problems with this model. It had the wrong unstable growth rate, some bad long-term stability properties, things like that. And so 2 weeks after that, he emailed me again and told me that he basically fixed it. And so I want to tell you about the 2 ways that JC kind of improved these models for physical systems, because I think this is a really good lesson for all of us that do physics-informed machine learning. There are some really great lessons here about how you can bake in partial knowledge of the physics to get way, way better models. So the first thing JC did was he pointed out that we were throwing a lot of information away when we were modeling this system. Sure, we didn't know the exact form of the differential equations we were going to get, but we knew we were dealing with an incompressible fluid system. And we know that those systems conserve energy, and specifically that they conserve energy because of a skew symmetry in the quadratic nonlinear terms. That's a lot of partial information. That means that every model from an incompressible fluid flow simulation will have the skew symmetric quadratic nonlinear terms. And it turns out that you can enforce that skew symmetry in our SINDy models with essentially 1 extra line of MATLAB or Python code just by adding these equality constraints through a Lagrange multiplier formulation. So 1 more line of code, and essentially we get models that by construction have the same symmetry as the true dynamics and enforce energy conservation and have improved stability. The second innovation JC brought, which I think is really cool, is our models only had quadratic nonlinear terms because that's what the Navier-Stokes equations had. They're quadratically nonlinear. But JC pointed out that if you allow yourself to have higher order terms, cubic, quintic, septic, nonic, 3rd, 5th, 7th, 9th order terms, you can essentially account for very low energy modes that you have truncated, that you have neglected in the model. So remember, X and Y are the amplitudes of POD modes 1 and 2. These capture about 95% of the energy of my flow, but there are a lot of other modes, modes 3 and 4, 5 and 6, 7 and 8, that are low energy that we've thrown away, but they're dynamically important and they affect variables X and Y. And so if you include higher order terms like 3rd, 5th, 7th, 9th order terms, you can account for the dynamics of those truncated low energy modes. And what this amounts to is essentially a closure model for this simple laminar flow. Now, whether or not this generalizes to turbulence is still an open question, but at least in this simple laminar problem, we are able to close the energy by including higher order nonlinear terms. I will point out that our colleagues are using SINDy now for turbulence closure modeling for RANS models and for climate closures, which I think is kind of neat. Okay, let's see how these models perform. So we have the cylinder flow and the cavity flow, two canonical fluid flows. And the column on the right shows this A delta, that shift mode parameter. This is the coefficient of the shift mode. For you in the audience, if you're not into fluids, you can think of this as the drag coefficient. It's a quantity I care about. If I'm flying a plane through the air, I want to track the drag coefficient. And the white curve is the true the true value from direct numerical simulations, the ground truth. And the yellow and blue are the industry standard best models, those kind of 2003 models with 3 or 7 POD modes. And you can see that they're qualitatively okay, but quantitatively quite inaccurate. They have the wrong rise time, steady state error, and overshoot. Whereas our cubic constrained SINDy models almost perfectly match the rise and transience and evolution of these observed dynamics. So they're much more quantitatively accurate. What's important is that these models are not just accurate, they're sparse. And so you can actually take these models and write them down on a piece of paper and take them to a Paris cafe and analyze them and play around with them. And that's exactly what JC did. So JC took the SINDy model that gave this near perfect reconstruction and manipulated it into this simple form in blue. So this model essentially is the actual model for the cylinder flow that gives that perfect reconstruction. And it says that the dynamics are a spring mass damper with nonlinear damping, essentially a van der Pol oscillator. And so I can't emphasize this enough. The sparse models are not just accurate, which is good, they are human interpretable. You can analyze them, you can do differential equations analysis on these and say something new about the flow. To date, this is the simplest and the most accurate model of these two flows that have been written down, which I think is saying something. Something else that's kind of neat is that if you apply this to more complex flows like this 3 pinball cylinder configuration, you don't always need to have full measurements of the fluid velocity field in the wake. That's pretty unrealistic. When you're flying an aircraft, you don't have full measurements of the wake. Neither does the moth or an insect or an eagle. Instead, you might only have measurements on the cylinder surfaces. So in this paper, we showed that you can take just the lift and drag measurements on these 3 cylinders, and you can build these sparse nonlinear models directly in lift and drag coordinates, which is pretty impressive. That means that you don't need the full velocity field, and you can start building these models almost in whatever coordinate system you want, as long as it has enough information to describe the dynamics. Okay, good. So since this is not a fluids talk, I'm not going to go into all of the fluid examples we've looked at. I'll just kind of throw up a highlight slide that shows, you know, I've told you about 2 of these examples so far, the flow past a cylinder and the pinball. We've also applied this to chaotic electroconvection, plasma physics and fusion reactors, lid-driven cavity flows, and fully turbulent wake dynamics from experiments. And in all of these cases, we've been able to learn good low-dimensional coordinates x so that we can get sparse differential equations that are human interpretable to describe these dynamics. So if there's time in the questions and you have any questions about these, I can dive into little vignettes and tell you more. But what I want to do now is talk about the coordinates. All of the models I showed you, we started with a good set of measurements x. The x in our differential equation was handed to us. Either we knew it from the Lorentz equations, or we knew it from Bernd Nowak's 2003 paper, or we got lucky and we just used lift and drag, and that was a good x coordinate. So what happens when I am analyzing a new system like the brain, where I don't know what the right coordinate system is? Okay, so going back to this deep autoencoder picture, where we kind of are building in our autoencoder to also have dynamics, I think this is a very powerful picture for how we should be thinking about learning coordinates and dynamics. So we know that we want sparse SINDy models in the latent space z dot equals f of z, but how do we get that good coordinate system when I have bad measurements x or complicated measurements x? And so this picture is essentially supposed to make you think of a deep neural network autoencoder That's what this is here, to go from a high dimensional state X to a low dimensional latent space Z, this information bottleneck that encodes as much information about X as possible. And if you had a linear autoencoder with a shallow linear autoencoder, this would learn the singular value decomposition, the principal component analysis. But if you allow yourself to have deep nonlinear layers, then you can learn these nonlinear manifolds where your data evolves. And I want to point out that without the coordinates phi, it's often hopeless to learn a good dynamical systems model F. And I like to go back to this historical problem of how we learned F equals ma. So this is the picture of the universe. This is how we find ourselves in the universe. When you look up at the night sky, you're in this blue dot, that's Earth. And when you look up at the night sky for all of human history, when you look up, this is what you see. It's pretty messy, pretty kind of chaotic. The planets often don't go in perfect circles. They turn around in their orbits and do retrograde motion, and very hard to explain things. In fact, this is why we deify our planets, is because they have agency. They do whatever the hell they want to do in this coordinate frame. And sometimes it takes changing coordinates. So just moving ourselves so that the sun is at the center instead of us. Now everything becomes much, much simpler, and we can start to learn real parsimonious dynamics like F equals ma. So this is just a cartoon to show that sometimes you need to be in the right coordinate system to learn kind of the right dynamics, the simple dynamics, okay? And this is the idea behind this work by Kathleen Champion when she was a PhD student with Nathan and me, when she essentially combined the SINDy modeling procedure with a deep neural network autoencoder. So you use the deep neural network to learn a coordinate system, and that coordinate system should be such that in the latent space Z, a sparse differential equation describes the observed dynamics. Now, what we tried first was just learning the coordinates with an autoencoder and then sequentially learning a SINDy model. This doesn't really work because the autoencoder kind of warps the coordinate system into a very kind of non-interesting, non-symmetric coordinate system where it's very hard to learn SINDy models. So what we found in this procedure is that you actually have to do a joint learning of the coordinates and the dynamics simultaneously. It's much stiffer, and it requires these custom loss functions that guide both the autoencoder and the SINDy model. And we've applied this to a number of systems, and it actually is able to learn dynamics from things like video footage. This is what my friend Nathan calls GoPro physics. If you just have a GoPro kind of watching the world, can you learn low dimensional kind of parsimonious physics from that? And the answer is maybe. Okay, so that's this deep autoencoders for dynamics. What's interesting is that you can actually over-constrain this. So what we have constrained is that this is a sparse dynamical system. You can constrain things even more to ask for a coordinate system that perfectly linearizes your dynamical system. That's a lot more restrictive, and it's related to the Koopman operator. So this is work by Bethany Lush when she was a postdoc with us, where essentially Bethany, in the same deep autoencoder framework, learns a coordinate system in which our dynamics appear to be as linear as possible for as long as possible. And there's a lot of issues with this Koopman theory. There's a lot that we don't know. There's a lot of kind of engineering knowledge that's needed for how to build these coordinate systems where your dynamics are linear. And if you're interested in how you might do that, we wrote this review paper recently. I think it'll be out in the SIAM review later this year, kind of how this fits into this Koopman perspective of linearizing nonlinear dynamics. Good. Okay, so I think what I want to tell you about now is a slight departure, but it's related to Koopman, it's related to coordinates, and it's related to SINDy. But it's brand new research. We just put this archive paper out a couple of weeks ago, and it's something I really want to tell you about. So finding good coordinate systems is challenging. Autoencoders is one perspective when you have really high dimensional data. If I have a big data set, like a full fluid flow field or a movie, of my physics, I can use these autoencoders. But what if I'm in the other regime? What if I have my complex system like Lorentz, but I only measure one variable? And so there's this latent space, this set of hidden variables that I don't have access to. That's much more common in observational science, right? There's lots of times where, again, my wife is a neuroscientist. When they have brain recordings, they're not recording 100 billion neurons. They might be recording 100 if they're lucky, okay? So what do we do with these latent spaces? So assume you measure just the X variable in this Lorentz system. In this 2017 paper, we showed that if you build a Hankel matrix, if you time delay embed your scalar measurements into this Hankel matrix, so X at time 1, time 2, time Q, and then you take its singular value decomposition, you can essentially, through Tocken's theorem, learn kind of an Eigen time delay coordinate system that captures a lot of the same structure as your original system, even though you didn't know what it was. So this is what the time delay coordinates look like, these Eigen time delay coordinates. And you can see that it's kind of topologically similar to my original Lorentz equations, which is what Tocken's tells us we should be able to find. Now, in this problem, you can learn a coordinate system, but in that coordinate system, there's no guarantee that we'll get a dynamical system that is sparse, that's nonlinear, that has anything to do with the Lorentz equations, because we fundamentally don't know what y and z are. We've never measured them. So how can we start to use these techniques I've told you about to learn parsimonious interpretable dynamics on that latent variable v? Okay, so this is the new paper by Joe Bakerjee, where we essentially combine everything I've told you, time delays, autoencoders, and SINDy, to, I think for the first time, actually learn things like the Lorentz equations purely from from partial measurements. So I want to walk you through this. So we assume we have something like the Lorentz system where we only measure one scalar variable. We're going to do a time delay embedding into a space where we get kind of the topological information we need. And then the blue circles is what we're going to learn with machine learning. We're going to learn a coordinate transformation through an autoencoder and a sparse SINDy model. So essentially everything on the right is that SINDy autoencoder from Kathleen, but we're going to apply this to time delay embedded data. And so Tocken's was in 1981. And in the last 40 years, we have not had a path to write down the diffeomorphism between the delay embedded attractor and the original attractor. And this is giving us a path to finally do that. So if we have our unknown system like this Lorentz dynamics, but we only measure the X variable, we're going to take that time delay state and compress it into an autoencoder to learn a latent representation Z, where we can get Z dot sparse dynamics. This is an extremely stiff optimization. What I'm going to tell you is that it is possible, but it is not easy. And we've learned a lot in trying to make this optimization work. It's not an easy optimization, but it does exist. There is a solution. And so in doing the SINDy autoencoder to our delay vector, what I'll point out, the blue attractor is the original Lorentz attractor. The yellow or gold attractor is the new discovered latent representation. And those equations on the right are what Joe discovers. Now, I want to just stop for a minute and point out the equation on the right is actually more sparse than the original Lorentz equations. So Lorentz has 7 terms. Our discovered system on the right has 6 terms in the dynamics. It is actually a simpler, sparser model, which kind of surprised us. We were not expecting to get less than 7 terms. Now, our model has more nonlinear terms. Our model has 4 nonlinear terms and 2 linear, whereas Lorentz has 5 linear and 2 nonlinear. So it's simpler in one way, it's sparser, but it's more complex in another way. It has more nonlinearities. But I think this is kind of remarkable. Purely from measurements of X alone, we learned a coordinate transformation where we could get sparse, interpretable dynamical systems. You'll also notice that some of these variables look like they are closely related. 2 of the coefficients have coefficient 8, another 2 have coefficient 16. So we're currently in the process of doing a bifurcation analysis to try to parameterize and continue this system to other parameter regimes. So anyway, pretty exciting times that from partial measurements, you can start to learn real nonlinear dynamics. And the last part I want to show you that kind of blew me away is this one here, where we have this video from Harvard. We just downloaded off YouTube of the Lorentz water wheel. So this is a mechanical system that has a lot of the characteristics of the chaotic Lorentz system. And essentially from video processing, Joe was able to extract this angular velocity curve. This is our partial measurement. And with the delay SINDy autoencoder, he was able to learn this kind of attractor on the right and a differential equation model that gave some of these observed chaotic switching dynamics. So that's pretty powerful. From a video, we can learn a low dimensional coordinate system and get our physics out. Okay, so that's most of what I wanted to tell you with the sparse nonlinear modeling perspective, how we can get interpretable and generalizable models for physics from data. Maybe the last thing I'll do, because I have a couple of minutes, is I'll tell you about this work by Jared Callahan on dominant balance physics. So dominant balance is a really important idea that goes way back in mathematical analysis. Some people might have heard this called asymptotic analysis in the 1950s and 60s, when applied math departments were growing up out of aerospace engineering departments. Before computers were powerful enough, if we wanted to analyze a system like this turbulent boundary layer flow, we would have to make physical arguments that in certain regions of space and time, some terms would be large and active, where other terms might be nearly zero and we could neglect them. And that would allow us to write down a simplified equation in terms of a dominant balance of a few terms where we could do asymptotic analysis. And so what Jared is going to do here is essentially automate this dominant balance procedure, just like we automated the Lorentz 1963 procedure earlier. So we're going to warm up on this boundary layer problem. You can download this data. It's open source from Johns Hopkins. And the first thing you might do is do a two-dimensional average and average out time to take these to get the two-dimensional Reynolds average Navier-Stokes equations. This is essentially a partial differential equation with 6 terms. And the hypothesis is that in different regions of space or time, different terms will be active and equal, kind of balanced, while others will be approximately 0. So for each term in the equation, you can compute that term and plot it everywhere in space. This is a spatial plot of that first term, u bar x. And you can do that for all 6 terms. And again, you can see with your eye that there are regions where some of the terms are equal and opposite, where the other ones are approximately 0. And what Jared realized that I think is really cool here, is that every point in space here, every spatial point has 6 numbers associated with it, 1 for each of these terms. And so for every point in space, each of our original spatial points, you can plot that in a 6-dimensional equation space. So I can scatter plot all of my points in the 6-dimensional equation space, where each axis is a term in the equation. And that's what I'm showing here in upper right, are just 2 slices of our 6-dimensional equation space. And every white point is a point in space from our original data. You can see already that it looks like the data lives on these sparse subspaces. And so what Jared did was he first applied a clustering algorithm, Gaussian mixture models, to find clusters in the data. And then for each of these clusters, for the red cluster, he applied a sparse subspace identification technique to find the subspace that best describes that red cluster with as many 0 coordinates as possible. Same for the purple, the blue, the green, and the orange. And so here you can see what terms are active for each of those clusters. The red cluster only has 2 terms active, the blue cluster has 2 terms active, and so on. But again, because every single one of those points originally was a point in space, you can plot these back in our spatial domain. And so on the bottom, this is our actual boundary layer, color-coded by what terms in the physics are active at the moment. And I think this is just super cool, is that you learn that there are these coherent regions, the viscous sublayer, the inertial sublayer, the transitional region. This took 100 years of really smart people to learn and characterize this boundary layer. But if you just do a data-driven analysis, it pops right out of the data that there are these different regions with these different dominant balance physics. And in fact, you could do things like asymptotics at the interface of the blue and the red region, for example. And we have not just done this for the fluid systems we know the answer for. We've applied this to supercontinuum lasers, really high energy lasers, geophysical flows like the fluid flow in the Gulf of Mexico for getting climate regions where different weather patterns might be observed. And we're also applying this to neuroscience systems, both single cell and full brain type data. So anyway, I really wanted to show you this because this is a different take on interpretable kind of generalizable physics modeling that also is based on sparse kind of parsimonious models that I'm pretty excited about. This is, you know, hot off the presses just from last year. And again, all of this code is always open source online, so you can try it out yourself. Okay, so I think this is a good place for me to stop and just summarize that, you know, we have these powerful tools in machine learning and we should use them. We have a ton of data, but I don't just want kind of opaque end-to-end neural network solutions. If I can get an interpretable, generalizable differential equation model, that's better for me in a lot of cases. That's more what I want. And oftentimes we can get those by promoting low dimensionality and sparsity in our machine learning regressions. Okay, so I'll stop here and hopefully there's some time for questions. Thank you all.
Thank you, Steve, for this very wonderful lecture. Thanks a lot. And we have some time for questions. So maybe we start with Jürgen. No? Oh.
Okay. When you ask me, I have a question. Your applications, what you showed us, were rather lab experiments. But in the last, you mentioned Gulf of Mexico, bursting neurons. You have always noise, whatever origin it has. Can you also apply your approach to such noisy data?
Great question. Noise is a huge problem. It's maybe one of the biggest problems. So I've told you the first problem is getting the differential equation. The second big problem is finding the coordinates where you can get a differential equation. Probably the third big problem is noise. So that's definitely one of them. And this algorithm is a little bit over 5 years old now. So a few years ago, I would have said noise is the biggest challenge we have. But fortunately, in the last few years, there's actually been a lot of big advances that have allowed us to handle noisy systems. So the first set of advances is an innovation by Hayden Schaefer and then later by Roman Grigoriev's group that's essentially called integral or control volume SINDy. So you can basically integrate up over randomly chosen control volumes and then apply the SINDy regression library. And this averages out a tremendous amount of the noise. So for partial differential equation discovery, things like in the brain or in noisy experimental data, you can handle hundreds of times more noise than we could handle before just by integrating over control volumes first. And our postdoc, Urban Faisal, recently showed that you can also use robust statistics like ensembling and bagging and things like that to get, you know, an even higher noise robustness. On a different side, sometimes our physical systems, the measurements are not contaminated by noise, but by multi-scale processes that we can't resolve. These are actually disturbances like turbulence or, you know, in the brain, real things that we just can't resolve. And so in that case, Jared Callahan has generalized this framework to stochastic system identification. Mm-hmm. So maybe we have coherent structures in X, so we have this drift diffusion kind of dynamics, but we also have to account for this correlated in time or correlated noise forcing sigma. And so that's something he was able to do essentially for full turbulent wake experiments. This is George Regis's data from Imperial College, where, I mean, this is, you know, Reynolds number million experimental turbulence data, and we're able to get pretty good SINDy models from that data. So that was, before that, about a year ago, I would have said, no, this is, you know, impossible if it's fully turbulent, you know, maybe not, but I was blown away that they could get this model working for that kind of data. Great question.
Interesting. Thank you.
Yes, go ahead, please. Go ahead, Louis.
I didn't want to type everything because it would be too long. First of all, excellent talk. It was a pleasure to see a machine learning talk that actually had physically interpretable results. It may be a rarity. Maybe I haven't been around enough to see that, but that was good, and I really liked it. But I do have a question about the embedding parts when you're talking about using Tocken's theorem, because partly because that's what I know the most about.
Yes.
And that was very impressive. But it's obviously you're just in the beginning stages, because there's the standard problems of finding the delay and the dimension of the actual attractor from data,
Yes.
and that's still is a standing problem, unsolved in any optimal way that I know of. And I've taken some shots at it, but it's hard. I'm just wondering if you've done anything along those lines, and how do you determine the time delay? How do you, without knowing, you started by knowing the system. Now you're given data, you don't know the dimension, you don't know a good time delay. Often there are many time delays because you have different time scales. So have you gone at any of that, and do you plan to?
Fantastic question, and thank you. Yeah, so when I was presenting this, I could see in the audience, it's a little intimidating because there's some real heavy-hitting figures from dynamical systems who have done a lot more work on this than I have, actually. So I think you said it well. We're really in the introductory stages of applying this, and honestly, I think we got really lucky. I'll tell you the truth. So my postdoc Ulrike Kaiser, she's trained in kind of classical dynamical systems also, and she's much more familiar with, the information theory of how to choose the embedding dimension and the delay times. And, this seems like a very difficult procedure in general to tune, to identify. We got lucky in the sense I came from a control theory background. And what we do in control theory is we build these Hankel matrices of time delays and take the singular value decomposition. And it turns out these are usually pretty decent coordinate systems. They're probably not optimal in some of the senses of like information captured and embedding and things like that. But these typically do capture information in a way that requires a little bit less knowledge of the system and a little less tuning. And so there's criteria for how to choose the number of modes, through machine learning cross-validation and things like that. And actually, this is one of the areas I think is interesting, is if we start with a manifold that's not ideal, that's not perfect, but it's kind of good enough, it has enough information, that might be an interesting starting point for some of these, now we're going to learn with machine learning a transformation where things get better. We were really fortunate also, we've had a couple of theoretical papers on these Eigen time delay coordinates. We were really lucky to have a couple of fantastic students come through that with really kind of high-end math chops, who started to explain why we were seeing what we're seeing in these Eigen time delay coordinates, these SVD coordinates. One of them related this to the Frenet-Serre coordinate system from differential geometry. And that's actually a really rich vein of work that I think we've only written one paper on it, but I'm really excited about that connection.
Where was that paper?
I believe that was a Royal Society A paper, and the lead author was Seth Hirsch.
Okay, good. Thank you.
Yeah.
Okay.
Yeah,
Steve,
great question.
Lots of questions in the Q&A box. Do you want to look at them and answer, or should I read it out for you?
Sure. Let me see. Okay. Okay, so I presented mostly results for autonomous systems. Are there results for nonlinear input-output systems or non-autonomous systems? That's a really good question. So maybe I'll go to a diagram here, because this kind of shows SINDy pretty well. Can everyone see the slides okay?
Yes. We can see.
Okay. Yeah, so in this library generation procedure, I've shown you kind of the simplest version of this, where you just have the state, in this case, X, Y, and Z, or Z1, Z2, Z3. But if you have external or exogenous variables, like a control variable U or time, you can include columns for those control variables, for bifurcation parameters, for time. And so you can generate systems that are time varying, that are actively forced, or that include bifurcation parameters. And we've done this in a few papers. So we've learned systems that are actively controlled by bifurcation parameters, like the logistic map, or like the flow past a cylinder. But that would happen in this library building stage. Great question, thank you. Is it possible to get a low order model for the reacting turbulent gas flow if one has noisy pressure, time series, or velocity? That's kind of related to that stochastic differential equation model I was showing. I would say it's not impossible to get a model of turbulent gas flow from pressure measurements, but it's going to be very challenging. And in general, I don't see this SINDy procedure as being a turn crank procedure. Okay, so one of the things I like about dynamic mode decomposition is that it's pretty easy to use. You put your data in, you turn the handle, and you get modes and eigenvalues out. And it's pretty easy to use and interpret. SINDy is a little bit more complicated. It's a tool that an expert modeler uses to get models they might not be able to have derived in another way. So if you're an expert on this turbulent gaseous system and you have an idea of the symmetries of the form of the dynamics, you might have a shot at using this to get those models. But I don't think it's generally just like an automated turn crank procedure. Let's see. Would it be fair to refer to a low dimensional model as generalizable when it represents the dynamics for a fixed set of conditions? So if I understand your question, you're saying maybe my models aren't as generalizable as I'm saying if it's only true for Reynolds number 100 where I trained it. I think that's a very good point. We have tested generalizability in a number of ways. One type of generalizability is generalizable to new initial conditions to capture transients that you might not have seen in your training data. And even at one Reynolds number, like Reynolds number 100, we have shown that you can get generalization to new parameter values to new initial conditions you've never seen before. But as I mentioned before, if you include bifurcation parameters in your model, you can actually learn the system parameterized by the order parameters that you're measuring. And in that case, often you can go to Reynolds numbers you've never seen before. So Jean-Christophe Loiseau wrote a really nice book chapter showing that if you train on a couple of Reynolds numbers, you can actually extrapolate the dynamics to other Reynolds numbers you haven't seen before if you build your library in a clever way. Okay, and I realize we're at the hour, so maybe I should stop here and follow up on some of these offline. Not quite sure.
You could continue till you have time. I mean, I don't know when you have to leave, but up to you.
Okay, maybe I'll take one more question if I can find. Okay, so one question says, I'm wondering how you decided on the number of hidden states Z when reconstructing the dynamical system from just measuring X. Excellent question. Very kind of big part of all of this is choosing, how do I choose the dimension of this latent space Z in all of my autoencoder examples? And the good news is that we can rely on pretty simple techniques for machine learning to do this. So what I would almost always advocate is before you add in the SINDy constraint, before you add in all of these SINDy loss functions, first thing you do is just try to build an autoencoder to reconstruct the dynamics, okay? And then in building an autoencoder, there's pretty standard techniques in cross-validation. You have some holdout data, and you use that holdout data to see how well does a model with 2 variables, how well does a model with 3 variables do, 4 variables, 5 variables. And at some point, you'll see generally that your error either flattens out or actually turns around. And that gives you a pretty good idea of what the kind of latent dimension of your system is. So we use basically, simple techniques from machine learning to tune that latent space dimension. Okay, I actually do have to go, but I am so glad for all the great questions, and thank you all so much. I really appreciate it.
Yeah, thank you so much. There was a lot of audience, 220 people attending together. So thanks a lot for this very exciting talk. And I also enjoyed the question and answer session. And we look forward to the next talk on 28th February of Luis Picora. He's a pioneer in chaos control. Everybody is welcome. Thank you, Steve, once again. Great talk.
Thanks, everyone. Bye.
Okay. Thank you all.